Hello everyone, this is Professor Roman. Welcome to the 26th video in my video lecture series, An Introduction to Discrete Mathematics. At the end of the last video, we looked at this table. This represents our progress up to that point. And in this video, we're going to fill in this cell. We're going to look at multisets of size k taken from a set of size n with unrestricted multiplicities on the elements, meaning, of course, the natural restrictions. No element can appear less than 0 times, a negative number of times, and no element can appear more often than the size of the multiset. Okay, so as to notation, by analogy with binomial coefficients, there are two fairly common notations in use for the number of multisets of size k taken from a set of size n. And these are the two notations. I'm not that thrilled with the second one, so I will use the first one, which I like. And I would read this as n multi-choose k, okay, or some words to that effect. Okay. Now, since repetitions are allowed in multisets, there's no reason why the lower number k can't be larger than the upper number n. For example, one multi-choose 2 is the number of ways of forming a multiset of size 2 from a single element. So that element must be repeated twice. There's only one way to do that. The notations for multisets are not anywhere close to as widely known as the notation for binomial coefficients in choose k. So if you decide to write about these or speak about them to someone else, you probably will need to explain this notation. And you'll probably need to explain what a multiset is, because as I mentioned before, multisets are just not nearly as common as they should be. So suppose now that S is an underlying set with n elements. Since the order of the elements in a multiset is irrelevant, a multiset of size k taken from this set is completely determined by the multiplicities of its elements. So that would be the numbers m1 through mn, the multiplicities of each of the elements in the underlying set as they appear in the multiset. The sum of those multiplicities has to equal the size of the multiset. So in fact, the number of multisets of size k, again taken from a set of size n, is simply the number of solutions in non-negative integers to this equation. The mi's are the multiplicities, so it seemed to me that we should call this the multiplicity equation. Okay. Now we can view this equation in a different light as a division of the integer k into n distinguishable non-negative integral pieces or parts, m1 through mn. And distinguishable is an important word here. Just as with divisions and partitions of a set, which are very similar but distinct, because partitions require the blocks to be non-empty and the blocks are indistinguishable. For divisions, as I've been using it in this course, the division of a set is just a collection of subsets that are mutually disjoint and whose union is the whole set. And they are distinguishable subsets. Okay. I've never liked the term division in this context. It's probably because we're also used to thinking of division as an operation with numbers, but I don't know that there's a standard term here. Partitions is a standard term, so I've chosen divisions to mean, the other option. There are both divisions and partitions of an integer, and the distinction in the case of an integer is simply whether the parts are distinguishable or indistinguishable. There's no analog of non-empty, and there's no analog of mutually disjoint. So we don't have to worry about those aspects. So for example, these two equations, 1 plus 2 equals 3, 2 plus 1 equals 3, are different divisions of 3 into two parts. Okay, different solutions to this equation. It would, in this case, it would be, say, x plus y equals 3. Two different solutions. X equals 1, y equals 2. X equals 2, y equals 1. But as partitions of the integer 3, these are the same. Okay, because the parts are indistinguishable. So you can reorder the terms in the sum any way you want. It doesn't change the object. I'm going to discuss partitions of an integer much later in the course, because we're going to see that life is rather more complicated when the parts are indistinguishable. Generally speaking, that's true for indistinguishable parts. As a matter of fact, there's no known simple formula for the number of partitions of an integer. But for now, we're going to just deal with divisions of an integer. And in this case, there is a one-to-one correspondence between the family of multisets of size k, taken from a set of size n, and the solutions in non-negative integers to the multiset equation. Okay, because the multiplicities completely determine the multiset. So there are as many multisets of size k as there are solutions, ordered n-tuples now because we're distinguishing the parts, in non-negative integers to the multiplicity equation. So we can forget about sets, multisets, and all that and just concentrate on a simple equation, the multiset equation. How many solutions are there? How do we count the number of solutions in non-negative integers to the multiplicity equation? Well, a common technique to counting any structure that we might be a little confused about how to start is to try to relate that structure to a different structure that we already know how to count. And in this case, to see what that structure might be, it's a good idea to start with a simple example. So here's a very simple multiset equation. There are 3 parts, and they have to add up to 8. So here are some solutions. How can we express these solutions in a different way that might help us count the number of solutions? Well, there is actually quite a simple way. We can do it with 2 symbols. And I'll choose x and a slash, /. 134 could be written x slash xxx slash 4x's. And 206, 2x's slash 6x's. And similarly for 080. So the idea is there will be 8 x's, because this number k is 8, and we will separate them by slashes in order to represent the different multiplicities. Okay. Well, these are just words of length 8 plus 2, 8 x's and 2 slashes. So that's 10. Words of length 10 over this alphabet of size 2. Any solution to the multiplicity equation can be written as a word of length 10 over this alphabet, and any word over this alphabet gives us a solution to the multiplicity equation. This is a one-to-one correspondence. We can generalize that very simply. A solution to the general multiplicity equation is just, or can be represented by, a word over the same alphabet where we start with m1 x's, then a slash, then m2 x's, and so on. There are k x's total because the multiplicity equation has a k here. And there are how many slashes? Well, since the x's are grouped into n groups, one for each multiplicity, you need n minus 1 slashes to separate those n groups. That's important. So you get words of length k plus n minus 1. A lot of students will get confused and think it's k plus n. It's k plus n minus 1 because you need one less slash than you have groups. So we have a one-to-one correspondence between the following three sets. The set A of all multi-sets of size k taken from a set of size n. The set B of all non-negative integral solutions to the multiplicity equation, which I've been writing as an ordered n tuple. And the set C of all words of length n minus k plus 1, consisting of k, x's, and n minus 1 slashes. Well, we already know how to count this last one. The number of words of length k plus n minus 1 over an alphabet of size 2. The multiplicities are for x it's k, and for the slash it's n minus 1. It's the multinomial coefficient. N plus k minus 1, k comma n minus 1. And that's a binomial coefficient. N plus k minus 1, choose k. So we have our formula. And this is simply a repetition of what I just said. And we can now fill in this cell in our table. The subject of integer solutions to equations, such as the multiplicity equation, is very important. But I'm going to postpone further discussion of that to the next section, because I want to concentrate now on the matter at hand, which is multisets. Okay. So the number of multisets of size 12, taken from a set of size 7, 7 multi-choose 12, 7 plus 12 minus 1, choose 12, 18 choose 12, 18,564. Now an important example. A candy store sells 6 different types of chocolates. How many ways are there to fill a box with chocolates if the box holds 10 pieces? The order of the chocolates is immaterial. Well, filling the box with chocolates amounts to choosing a multiset of size 10 from a set of size 6. No restrictions on multiplicities except the natural ones. You know, you can't put 11 pieces of candy in a box that only holds 10. So 6 multi-choose 10, which is 3003. Now I'll get serious here. See's candy stores, which are, I think, ubiquitous in the United States, carry approximately 60 different types of chocolate pieces at any given time. The amount fluctuates with the season, introduction of new types, and so on, but let's just say it's about 60. A 1-pound box can hold roughly 25 pieces. Again, that depends on the size and weight of the pieces. So there are a total of 60 multi-choose 25, or 84 choose 25, which is 1.5 times 10 to the 21 power of different chocolate assortments. This is also 1.5 zeta different assortments. I've only tried maybe half of these, but if you want more information on the prefixes for powers of 10, zeta and iota and exa and peta and all that stuff, you can find it here, a Caltech website. So I included this in case you're interested. I didn't realize there were so many of these myself until I checked it out. Okay, now back to something really serious. No more chocolate. Well, they may come up again, but anyway. We've made considerable progress in counting arrangements of different types. And let me go back here to the table. We've done pretty well. Unrestricted multiplicities, fixed multiplicities, no multiplicity, no duplicates, multiplicity 0 or 1. But things are going to get a little bit more complex now. The general case is to count words or multisets of size k over a set of size n whose multiplicities must satisfy both either lower and upper or both bounds. So it looks like this. It's going to take us a while to produce some formulas in more general cases than we've done so far. But we're not going to have any luck with words. We will have some luck with multisets. Okay. Nevertheless, there are some things we can do now, so that's what we're going to look at. For multisets, the lower bounds on multiplicity do not cause any problems, and I'll show you that in a minute. The upper bounds, however, do present some issues, and we're not going to be able to deal with those issues until much later in this course. Okay. We need some more mathematical machinery. But as to dealing with the lower bounds, in the general equation, multiset equation, we would have these bounds. Okay. But if we take the sum of the lower bounds and subtract that number, L, from both sides of the equation, writing it this way, so m1 minus L1 plus all the way up to mn minus Ln equals k minus L, we can now replace the stuff in parentheses. So mi minus li, we'll just call it mi. You can pick a different letter if it bothers you to do that. We get a new multiplicity equation. And the bounds now are these. So the lower bounds are gone. They're replaced by the natural lower bounds. Okay. And there's a one-to-one correspondence between the solutions to the original multiplicity equation with these restrictions and the solutions to the new multiplicity equation with these restrictions. So we haven't lost anything, but we've managed to remove the lower bounds, the unnatural lower bounds. So looking then at a problem of solving the multiplicity equation with just lower bounds, no upper bounds except the obvious one. The multiplicity equation here has this many solutions, n multi-choose k minus l, which could be written this way. So, theorem, we have a set of size n, the number of multisets of size k taken from that set with the property that the multiplicities of each element are bounded from below is this value. And it's n multi-choose k minus l. If you don't want to memorize this, and I don't blame you, you should be able to reproduce this argument fairly simply. The only thing you have to, well, if you want to call it memorize, you can, is when you're faced with lower bounds, just subtract the lower bounds from both sides. Example. Oh boy, here's more chocolate. You might think I'm obsessed with chocolate. I'm not really. Sort of. Referring to the previous example, the number of ways to fill a chocolate box with 10 chocolates from 6 types that are available, including at least 2 dark chocolate covered almonds and 1 caramel patty, will look like this. If you didn't have the restrictions, it would be 6 multi-choose 10, but you have to subtract the lower bounds from the bottom number, from the lower number. And one of them is 2, the other's 1, so you subtract 3. Then remember, it's upper plus lower minus 1 goes here, and you repeat the lower one. And it's 792. Suppose that a certain exam is being given on 3 consecutive days, and 25 students are required to take the exam. In how many ways are there to assign each of the students to one of the 3 days, assuming that at least 5 students must be assigned to each day? So you have, let's say, you want to make sure that on no day there aren't enough students to bother to monitor, give the test. Okay. Well, so assigning the 25 students to 3 days with these lower bounds amounts to choosing a multiset. I wrote combination here for some reason, of size 25 taken from this set of size 3, the 3 days, where each day must be chosen at least 5 times. So 3 choose, instead of 25, 25 minus the sum of the lower bounds, 15. 3 multi-choose 10, which is 3 plus 10 minus 1, choose 10, 66. there is one case we should single out, and that's where the boundary conditions are these. So this means essentially that every element of the underlying set must appear in the multiset. And so we have this corollary. The number of multisets of size k taken from a set S of size n, where each element of S must occur at least once, is n multi-choose k minus n, which is k minus 1 choose k minus n. Okay. And simply because all these are 1, there are n of them, so that's why we subtract n. Well, now we can fill in 2 more cells here in our table. The theorem we just gave, let's see if I updated the numbers here correctly. Okay. Theorem 266, which is our main theorem here, fills in this cell. These are the multisets of size k taken from S with general lower bounds, no upper bounds. Okay. And the corollary gives us this cell, multisets of size k taken from S, where all elements are used, so the lower bounds are 1. What we're left with is to deal with these 3 cells. And it's going to take us a little while to build the machinery we need to take care of those. But what I want to conclude this video with is the promise I made earlier to briefly return to the subject of integer solutions to linear equations, because this is an important topic aside from its involvement with multisets and multiset coefficients. Nonetheless, what we're going to do in the next couple minutes is just a rehashing of what I've already done with a different language. It won't take long, so it's worth bearing with me. First, some terminology. An equation of this form, where k is an integer, is called a linear equation with unit coefficients. Conditions placed on the solution that are of this form are referred to as boundary conditions. This set of inequalities are called the lower boundary conditions. This set is called the upper boundary conditions. We allow the lower bounds to be negative, which we don't do for the multiset case. And we also allow the upper bounds u sub I to be equal to infinity, which effectively removes that upper bound. Okay. Incidentally, this reminded me, there is a paper somewhere, I don't know if I can find it or not, but it's entitled Sets with a Negative Number of Elements. So that is kind of, I guess, related to lower bounds that are in fact negative, but it's a strange paper as I recall, and I wouldn't make too much effort to try to find it. Okay. Anyway, our main interest is in determining the number of integral solutions to a linear equation with unit coefficients that satisfies given boundary conditions. The technique that I described earlier, that I called lower boundary translation, works just fine if the lower bounds are negative. And so that gives us the following theorem, slightly more general than the version for multisets. In the general case of a linear equation with unit coefficients and general boundary conditions, the number of integral solutions is the same as the number of integral solutions to this equation, where I've again subtracted the sum of the lower limits. Okay. And that means the range of the variable has to be adjusted. Whatever you subtract from the variable, you have to add to the range of the variable. If there are lower bounds only and no upper bounds, so the boundary conditions just reduce to this, the number of integral solutions is the multi-set coefficient n multi-choose k minus L. If the lower bounds are equal to 1, as we just got through talking about, is that corollary, then the number of integral solutions to this equation is this multi-set coefficient, n multi-choose k minus n. And if the lower bounds are 0, then we're in the case for the multisets, and we just get n multi-choose k. So a couple of examples. The number of integral solutions to this equation with these boundary conditions, we have x plus y plus z equals 12, is the same as the number of integral solutions to this equation. If you add the 3 lower bounds, you get 5. Subtract that from 12. That reduces this to 7. And then you have to adjust the boundary conditions so that the lower bounds all become 0. And I'll let you complete this example and get the actual number. The number of non-negative integral solutions to this equation is 10 multi-choose 15, which is 24 choose 15, 1,307,504. So these are the non-negative integral solutions, no, just the natural lower bounds. But if we insist that the variables be positive instead of non-negative, that means each of the lower bounds here is 1. We have 10 of them, so we subtract 10 from the lower number. We get 10 multi-choose 5, which is 14 choose 5, which is 2002. It seems a little bit of a surprise. Switching from non-negative to positive solutions really drops the number of solutions dramatically. How many integers are there between 0 and 999,999 inclusive with the property that the sum of their digits is equal to 5? Now you could do this directly. You could take the case where one of the digits is 5, and that could be placed in any one of 6 places and fill the rest with zeros. You could take then the case where one of the digits is 4 and one of the digits is 1, and you'd have to figure out how many possibilities there are for that, and so on. But it's much easier to do it as follows. Each integer in this range can be written as a word of length 6 over the alphabet of digits. Now, some of these digits will never appear because we have this, we're looking for solutions to this equation, so you can't have any 9s, 8s, 7s, or 6s, because these must all be non-negative. Okay, so the number of such integers is equal to the number of non-negative integral solutions to this equation, and that is 6 multi-choose 5, which is 252. Much easier than doing it by brute force, you might say. One last example. The number of integral solutions to this equation with these conditions: x1 bigger than 5, x2 bigger than 0, x3 bigger than -2, x4 bigger than 6, is this multiset coefficient, and I'll let you sort out exactly why that's true. Okay, I think that's enough for this video. In the next section, we're going to talk about distributing balls into boxes, part 1. And so this is a common way to describe certain combinatorial problems that's a little different from what we've done so far. Thank you for watching this video, and I hope to see you in the next video.